So let's say again those announcements. Number one, you know about student course evaluations? Yay? Have you done them yet? Good. Okay, if not, please don't forget to do them. You can wait till you see that final grade if you want to, or whenever, but please do them before August the 8th. I wouldn't wait till August the 8th because I'm not going to be here to remind you on August the 8th to do your student course evaluation. I'd say do them sooner rather than later. Okay, sorry that I forgot to do these. For anyone who's just tuning in, we've already done, let's see, we started today at example 4 on page 325 in chapter 5, logarithmic, exponential, and other transcendental functions. 5.2, the natural logarithm function integration. We did the 4 parts of example 4. We just finished doing example 5, and then Patrick noticed I wasn't recording. So sorry I forgot to turn on the recorder. Okay, but now it's on. Let me go over how we're going to end the term. Okay? Today, because at least 2 people have to leave by 10, before 10 I'm going to return all your tests to you. So that means if you haven't turned in a test, get it in to me before 10 o'clock this morning because I need those in so I can return those to you. Okay. Then the rest of us will continue or whatever. And by the way, also if you weren't here last Wednesday, please get a copy of the last test before you go. That is your last exam. It's test 4. Mostly on chapter 4, there may be a few questions on chapter 5, okay? We'll see how far we get, and I don't think any of those will wind up being bonus because I think we're going to get covered what we need. Okay, so that's today. Well, that's for our class. Then I have class right after this at 11:30, and right after that at 2:30, but then I'm back in the office from 5:30 to 6 this evening, okay? What's my room number? Okay, it's room 265. But you go out the door here, hang a left, go down that little half flight of stairs right there, and go almost to the end of the hall. The last office on the left is 265. That's my office. So that's where I am today until at least 6 o'clock, probably a little after 6. Okay? Tomorrow, last day of class for Tuesday, Thursday classes. So I will be here from 8 to 8:30 in my office or getting ready for class. And then my class goes from 8:30 until 10:45. So from 10:45 until somewhere around 4:15, I will be in my office on this campus. Okay? 4:15 or so, I've got to leave to go to the Birmingham East campus to teach my last class of the physics class. That starts at 5 and goes till 6:30. So I'll be there a little before 5, so if that's convenient for you, you can bring stuff then. But otherwise, wait till after 6:30. I'll be there for usually close to a half hour after class as I'm wrapping things up, shutting systems down and stuff like that. So that will be tomorrow. Wednesday is the first day of finals, okay? So no classes on Wednesday. So I'll be in my office from 8 o'clock in the morning until 6 o'clock in the evening. Now, if someone needs me to come up here to the classroom, I can come up here. But basically, I'm in my office. So if you're going to bring something by to turn in, don't slide it under this door here. Bring it to my office, 265. I won't see it, and the cleaning lady may pick it up and put it in the trash can. So don't slide anything under this office door. This classroom door, make sure it's the office door, 265. So I'll be there all day. I'll also be recording everything, grading everything that's been turned in and getting Blackboard caught up and that kind of stuff. Okay, Thursday is the final exam day for Tuesday, Thursday classes. So I'll be in my office from 8 in the morning until around 4 o'clock. Around 4, I've got to leave here to head over to the Birmingham East campus again to pick up final exams there. Now, that day, anytime between 5 and 6:30, or maybe a little later, will be perfectly fine to bring stuff over to the Birmingham East campus. By the way, the room that I'm in over there is room 214. It's the nursing building, Ethel Hall, Nurse School of Health Professions, something like that, on the Birmingham East Campus, and I'm in that building on room 214. So you can bring stuff there. All right. That's Thursday. If I don't have your research papers and or test by the time I leave on Thursday, I'm not going to be here, or at least I'm hoping I'll be able to get leave for Monday. And I'm not planning to be here on Monday. So I need everything turned in later today, anytime tomorrow, definitely anytime on Wednesday. I'll even extend it to anytime on Thursday. But after I leave this campus at 4 o'clock or that campus at 6:30, I won't be able to pick up anything else. Okay? So please get me everything in by then. Now, I can't return your research papers to you, but I will be returning all your tests to you. I'll do that today before 10, so keep up with the time. All right, so this was example 5. We did it. Let's see how they did it. Began by using long division to rewrite the integrand, because there that's an improper rational expression, meaning the degree of the numerator is greater than or equal to the degree of the denominator. In this case, it's equal to, so you do your long division, and they didn't put the x term in here. I like to put a 0x there. They just had to leave a blank down here. But this will be x squared, and x squared will go 1 time. Now, I like to put that 1 over here, because then I see exactly where I am. But 1 times x squared is x squared, 1 times 1 is 1. Be sure you don't put this one under the x. That's why putting a 0x there is beneficial, okay? And then subtract. That goes away. This gives you just x, and those go away. 1 minus 1 is 0. So your answer is 1, division of 1 plus the remainder is x over x squared plus 1. Now, how do you know to stop dividing? Anytime your remainder is lower degree than your divisor, okay? And x is lower degree than x squared. Stop there and put it over the divisor. Now, since this thing here was in your integral, put this in your integral, okay? And chew on it. No. And that would then be the integral of 1 plus blah, blah, blah. And break that into 2 integrals. And here's Reginald, sorry. Now, I said this before, let me just quickly say it again. Everything has to be turned in to me today, because this is the last day of class. That means your research paper and your all your old tests, okay, previous tests, 1 through 3. If those aren't turned in, please get them to me before you leave class today. Now, if it's your research paper, after class today, you'll start losing points, but I will accept it later. But your test, I have to have in today, okay? Test 1, test 2, and test 3. In fact, I've already returned test 1 to this class, but I think Law was not here that day, so I wish I'd have thought of that this morning. I could have given you this earlier. Jasmine, oh wait, maybe I did give it to you. Nope, there you are. There's test 1. All right, thank you. Research paper. All right, good. 2 and 3. Okay, let me mark. Mirror in here. Ah, here comes another. Research paper, excellent. Okay. All right, Jasmine is true. Oh, goodness, this got an exodus going. Good. All right, good deal. Thank you. All right, so I've returned everyone's test 1 to them except Jasmine, but she withdrew from the course. Let me see now. I think I've now received all of test 2 in. Let me make sure. Reginald's. Jasmine through. Yeah, I've got them all. So let me go on while I'm thinking of it. I said I would do this later, but since now I've gotten all these in, I'm going to return these. Now, Amy's not here. Brian's not here. So Maya is. Is. Jalen's not here yet. Lyle is. Malcolm is. Terry is. The other thing I don't want to carry the paper problems. Okay. Joy's not here yet. Ashley's not here yet. Devin's not here yet. Patricia came by Patience came by this morning. I didn't know she wasn't coming. Come in here, or I would have given her hers. Mary is here. Okay. Now, let me just do a quick review on test 3. I don't have all of test 3 yet, so I'll give those people opportunity to come in. But for you who have to leave at 10, please let me know and I'll stop and return your rest of your papers to you at 10. Okay, did I get, yeah, I think I got everybody. 1, 2, 3, 4, 5, 6, 7. Yeah. Okay. All right. So we were continuing, for those who just came in, we're on example 5, which is in chapter 5, logarithmic, exponential, and other transcendental functions, 5.2, natural logarithm function integration, and example 5 is top of page 326. And we've already done it, and this is how the book is doing it. Once they did the synthetic division, they then split it into 2 integrals, integral of dx, which is just x, and then the interval of the next one, which they put a 1/2 in front and a 2x on top. That's perfectly fine to do if you like doing it that way. We did a U substitution and came up with the 1/2 out front, so we're same thing as got the same answer. And it's x plus 1/2 the log of x squared plus 1 plus c. Notice in this case, you don't have to put absolute value bars because x squared plus 1 is never negative, never even 0. So now, it says check that result by differentiating to obtain the original equation, integrand. Well, of course, that would be 1 plus 1/2 of 1/x squared plus 1 times 2x, chain rule, and that would be 1 plus 1/x squared plus 1, x over 1x squared plus 1. And then when you go back and rewrite that, you get it back into original form. You don't get it immediately, but you do another step. Okay. Now, before I get the guidelines for integration, let's step back one more and do example 6. Okay. We'll do that here. Any questions before we move to example 6? And because I shut down, got to go back and get another pen color. Okay, the next example present blah, blah, blah. Okay, we'll see. Find this definite integral. Okay, the integral of 2x over x plus 1 squared dx. Now, how would you proceed with that? I can think of a couple of ways to go. How would you do it?
Substitute x plus 1 squared.
Is it be u? Is that what you said? Okay. So he was going to go to the u substitution, let u equal x plus 1. Is that what you said? Okay, next. Then du is equal to? Dx, that's all, okay? But we have a 2x dx, not just dx. Have we got a problem here, Houston? Well, and we had one like this before. We can take care of this x here by solving for this x. In other words, subtracting 1 from both sides gives you u minus 1 is equal to x, right? Okay, so that takes care of the x. How we can take care of the 2 is multiply both of that second line by 2. And now we have 2 du is equal to 2 dx. All right, so the 2 dx is your 2u, so I'm going to put the 2 on the outside and do the integral. Okay, and the x then becomes u minus 1 over u squared. Okay, and that is times du, because the du was 2 du was 2 dx. We have our 2 dx, the 2 out front, and the du there is our 2 du. Now what would we do? Any ideas? Yeah, split up that numerator, okay, and make that u over u squared du minus 1 over u squared du, and make that a second integral. Everybody agree with that? You see that's legal in most states. Okay, now let's look at the first one, 2. And how can we simplify that integrand? Divide out a u, and that gives you 1 over u. What's the antiderivative of 1 over u du? Log of u, absolute value u. Perfect, okay? Minus, and how could you rewrite that second one? U to the minus 2 du, and that is fairly integrable, easily integrable. This would be 2, okay, remember the 2's in front of all that, okay, 2 times the log, absolute value u, minus so it'd be u to the negative 1 over negative 1, which will change that to a plus. And then we have one other thing, plus c. Well, we have something else to do. Let's get back to our x's, okay? This will be, I'm going to distribute the 2 across also. 2 times the log of, and what's your u? X plus 1. That needs to stay in absolute values, okay? Plus, and then I'll do 2, and what's your, 2 over x plus 1, okay, and then plus c. All right, x plus 1 is not guaranteed to be always positive, so therefore we'll leave it like that. All right, let's see how the book did. 2 times the log of absolute value x plus 1 plus 2 over x plus 1 plus c. They even left it in the same form we did. Now, on this one, however, I think I would have been very tempted to take the 2 and put it as the exponent here, and that way I could lose my absolute value bars. Then the log of x plus 1 squared Why can I lose the absolute value bars there? The squared is always non-negative, okay? And you just have to remember x can't be 0. But of course, I mean, can't be -1, but of course it couldn't have been -1 to begin with. So in our original problem, we probably should have said, comma, x cannot equal -1, because you can't divide by 0, ever, okay? So that would be log x plus 2 over x plus 1 plus c. I think I like that form better, just because it loses the absolute value bars for you. Okay, they didn't change that, but you could have. They have an interesting little blurb right before they get to guidelines for integration, because I think that's what's coming next. Yeah. As you study methods shown in example 5 and 6, be aware that both methods have involved rewriting a disguised integrand so that it fits one or more of the basic integration formulas. Okay? Throughout the remaining sections of Chapter 5 and Chapter 8, and in Chapter 8, which you'll do next term, much time will be devoted to the integration techniques. To master these techniques, you must recognize the form-fitting nature of integration. In a sense, integration is not nearly as straightforward as differentiation. Differentiation takes the form of, here's the question, what's the answer? In other words, here's the problem, how do you integrate it? I mean, how do you differentiate it? You just do that. Integration is more like, here's the answer, this is the result of integration, of differentiation, what was the question? In other words, what was the antiderivative? So here are some guidelines you can use for integration. Okay? First, learn the basic list of integration formulas. Your power rule, your logarithm rule, your sines, your cosines, your tangent, all the things there, your integration formulas. Okay? Find the integration formula that resembles all or part of the integrand, and by trial and error, try to find a choice for you that will make the integrand conform to the formula, which I would say, find the most difficult part of that integration, the integrand, and take the innermost part of that, let that be the u, okay? That just about always works. If it doesn't, try another one, okay? Continue with that. When you cannot find the u substitution that works, try altering the integrand. For instance, like we just did, that first one, you wound up still with an x up there, but you could rearrange the u in terms of x and get that to work, or x in terms of u, I guess it was. You might try a trigonometric identity, multiplication, division by the same quantity, addition or subtraction of the same quantity, long division. Be creative, okay? And if you have access to computer software that will find antiderivative symbolically, use it. I don't have access to that, so I like to do it. Check your result by differentiating to obtain the original equation, integrand, okay? So, here comes example 7. Solve that differential equation. Now, I sort of wish they wouldn't already call them differential. Why don't they just say integrate and make it an integral? Okay. Let me describe to you how I suggest you solve a differential equation. That's a derivative is equal to that. Rewrite that derivative as a differential. Okay? Call it differential equation. You can almost think of it that way. To write this as a differential, that would be dy is equal to 1 over x log x dx. It almost looks like you're multiplying both sides of the equation by dx. It really seems that way, and some people actually say that. A lot of mathematicians will cringe, won't they, Patrick, to hear something like that. What they really want you to do is write it in differential form. Now, we're not doing differential equations, but I'll suggest this to you. One, your first and simplest technique for differential equation is what they call separation of variables. Here on the left, you have your y's, only in the form of dy. On the right, you have all your x's. Okay? Well, a denominator x, the log in the denominator x, and the dx. So all your dx's are there, your dy's are there. So since you've got it set up that way, integrate both sides. Okay? And what's the antiderivative of dy? Y. Why not? Now, again, since you're doing two integrals, just wait and combine all the c's together. So don't do a plus c yet. But how about this one? My goodness, what do we do there? What do we do there? Anybody? What's your first guess? How would you proceed? U substitution. What would you use to be U? I like it. Log x. It's the most complicated part is your log x, and it's in the denominator anywhere, so let's just use that. Then it's always your next step. Du is equal to, I know it's been a long time, but what is the derivative of log x? 1 over x dx. Looky there. The 1 over x dx, there's your du, and then you have 1 over u. So this right-hand side becomes the integral of 1 over u du, right? And what's the antiderivative of that? Almost feels like we're running in circles, doesn't it? It's what? That is log absolute value u. Okay? Now, guess what? We go back and plug in, and so we have y is equal to, what is, this is log of, what was your u? Log of x. Now I'm going to put it in absolute value bars, okay? I'm going to put the whole thing in absolute value bars, and I'm even going to have to put the x in absolute value bars as well, and then do a plus c. Now, why do we need all the absolute value bars? Well, number one, the u is equal to log x. Log x could be negative, because between 0 and 1, a logarithm is negative. So you have to have that in there. But x, there's no restriction on x either, so it could be negative. Now, it can't be 0, obviously, because that wouldn't have made any sense at all. But it has to be. Now that I look at it, though, I think probably it's legal to take off the absolute values there. And the reason is, in the original problem, they didn't put x at absolute value. So that means x must be able to be positive, because they didn't have that. So I think I will go back and take out that innermost set of absolute values, because in the original problem they had a log x without absolute value, so that must make sense. But because that log x could be negative, you have to put that in absolute values, okay? And that's how they wound up leaving their problem. Y is equal to log of log x plus c. All right. And that's here. And it won't be long before I'll be returning all these to you, but just because you are here now, let me go on and give this to you. I have already returned to everyone their test 1, and I can't return research papers to anybody, but I did get the last test 2 in this morning, so that means I can return your test 2. Now, if people don't come in very soon, I'll be returning everything else pretty soon. 2 people have to leave at 10, is that right? And then I'll return everything to you. But you got to have, if you have it turned in a test, I need it in before the end of class today. Okay? So that was it for example 7. Well, that's what we did. Let's see how they did it, in case they did it in these ways slightly differently. Any questions before I erase mine? Okay. All right, the solution can be written as an indefinite integral, and they didn't show how you did, but they did this basically same thing we did. Write it as a differential equation rather than a derivative equation, and make the dy on one side, dx on the other side. When you integrate this, you get y, and when you integrate that, you wind up with this. Now, because the integrand is a quotient whose denominator is raised to the first power, you should try the log rule. Yeah, if you solve that, that would be fine. But Patrick, I think, was the one who suggested let's do a u substitution and let u be log x. And that works just as well, too. There are 3 basic choices for u. You could either use x, don't, x log x, don't. They both fail to fit the form u prime over du. So use the form u equal log log x. Okay? Letting u equal log x introduces then u prime, derivative of u, du, to be 1 over x dx. If you're going to do substitution, go on and do it correctly. Okay? And 1 over x dx is your du, and this is your du. So, if you had done that substitution, it's already done for you. They're saying divide first, now do the substitution or something. Seems sort of backwards the way they do it. Then they turn around and get this, which you could have gotten in one step the other way. Okay? And then that gives you log absolute value u plus c, but your absolute value u is log x, because that was your let u equal log x. So the log x is absolute value plus c. Now, the reason you don't have to put the x in absolute value bars, though we have been doing that, their original problem did not have it there, so you assume for this to be a legitimate form, x must be greater than 0. Okay? And with that assumption, you're okay. You do have to leave the log x there, because if x is between 0 and 1, that's negative, and you can't take the log of a negative number. Okay. So the solution is y is equal to log of absolute value log x plus c. All right. That was the example 7. Now they're going to do integrals of trigonometric functions. Now, we've already done some of these, so this is hopefully going to be mostly a review for you. Okay, I don't know why they come back and do them now. But what is the integral of tan x, tangent x? Where would you begin? Anybody? Integral of tangent x.
Change it to sine over cosine.
Okay, there would be a great first start. Let's rewrite that as the integral of sine x over cosine x dx. Okay? Then, that actually looks a little more complicated, but what can you note now? What would be your next step? Yeah, and what would you have? Let u equal what? Yes, the most complicated part would be the denominator. Cosine x, okay, then du is equal to negative sine x dx. Perfect. Hey, you've almost got your numerator and dx part as this without the sign, and then you got your denominator as the u. So to get rid of the sign, let's just do minus du is equals to sine x dx. So this integral in x becomes the integral of du over u. Right? And what would that be? Log of absolute value u plus c. Okay? Now, let's go back and plug in what u is. Negative the log of absolute value. What was your u? Cosine x plus c. Now, one other thing you can do here, this minus in front, you can make the exponent, and that be the log of, I'm going, yeah, okay. Okay. I was trying to figure out how many steps to skip. I guess I shouldn't skip any. Okay. That would be absolute. Come on. Okay. Okay. Absolute value cosine x to the minus 1 plus c. Okay? And then you could bring the minus 1 inside. And what is 1 over cosine? Anybody? Secant. That would be log of absolute value secant x dx. Okay. Now, fortunately, we have to leave the absolute value bars there, but you would also need to be very judicious in your choice of domains for the x. Okay? Here, because secant x is good from minus pi halves to pi halves, but not at either endpoint, you can do that. And so if you chose that, minus pi halves to pi halves, secant is always positive there, and you could lose the absolute value signs. If you chose pi halves to 3 halves pi, then you'd have to leave the absolute value bars in, because secant is always negative down there. So for me, I would say let's go for minus pi halves to pi halves, and then lose the absolute value bars. So if your domain for negative pi halves is less than, not less than or equal to, it can't even be that x is less than pi halves. No less than or equal to there. Anytime you have x in between that, secant is always positive. You can lose the absolute value bars, and that is a perfectly good answer. If the domain is not defined, then you have to leave absolute value bars in there. But you have to be within half pi's of each other. Okay. Now, how did they didn't even take it any further than this step right here. Okay. We took it a little further, but they left it right there. And that's a good answer. Nothing wrong with it. All right. Let's see how they did it. Okay. This interval does not seem to fit any of the formulas in your basic list. Okay. If you have that basic. However, by using a trig identity, you can obtain sine x over cosine x dx. And knowing that the derivative of cosine x is minus sine x, you can let u equal cosine x and rewrite this as the integral, negative integral of minus sine x dx over cosine x, which then would be exactly a minus u du, u prime du, u prime over du, okay. And that would lead to negative log u plus c, plugging in u being log or cosine x, you have negative log cosine x plus c. Now, they're skipping example 9, so let's go back and do example 9. However, we're pretty close to the time y'all have to leave, so my memory is there's some people who haven't turned in all the tests. Is that right? Okay, so I'm going to hold off. Are you going to turn in that test today?
Yeah.
Okay, before or now or later? No. Now, okay, I'll take it now. So everybody else is turning in all 3 tests, right? Yay? Okay, so let me return. Okay, Jasmine's not here anymore. Ryan's not here now. Ashley's not here now. Tarika's not here now. Test 4? Okay, good deal. Okay. And have you done the student course evaluation?
Yes.
You have? Good. Excellent. Okay. All right. Test 3. Amy's not here. Patrick is. So let me get up and move around a little bit. Okay. Jalen's not here. We'll go here. Law. Nelson. Okay. Gary. I'll have you there. Okay. Joy's not here. Ashley's not here. Patience came in earlier. I wish I'd have known she wasn't coming to class. I would have gotten you that. And Tarika's not here. Okay. Now, all right, I guess that's all. And it's not a bad time for a break. If y'all need a break, be okay with that? All right, well then let me turn off the projector, and we'll come back and begin with example 9. Okay. Let me turn on the projector as well. So, there was a question right before break, but I already turned off the recorder, so I wanted to say it again while the recorder was on. And that's going over how the term is going to end. Okay? I'm in class today from now basically until 5:30 with just a couple of little 5-minute breaks, and that's all. Okay, so, but then I'll be in the office from 5:30 until 6 today. Today's the last day for Monday and Wednesday classes. The day you've been dreading all term, the last day of class. Sorry about that, but get over it. Okay, now, tomorrow is the last day for Tuesday, Thursday classes. So I'll be in my office from 8 to 8:30 in the morning, or setting up the classroom here, which I usually do in that time too. Then I'll be in class here from 8:30 until 10:45, and then hopefully tomorrow I won't have to go to the Birmingham campus early like I've done for many of the last several weeks, both Tuesday and Thursday. For some reason, I've had to go to the Birmingham campus, so hopefully that was over for now, and I can just focus on final exams now for a bit. So anyway, that will be, oh, but let me say this. Tomorrow I do have an eye appointment at 2:30, right across the road here. So I'll be leaving the campus here between 2 and 2:15 to go over to the eye appointment, and then I'll come back and have to go to the Birmingham campus by 4:15. So hopefully the eye appointment will be over. Last time they kept me about 2 hours. Hopefully they won't be that late this time. Okay, so part of tomorrow afternoon I won't be available. If you come to turn something in and I'm not here, slide it under my office door. And my office is 265. You go out the door here, down that half flight of stairs, almost to the end of the hall, last room, office on the left is 265. So turn in anything you can. And if I'm at the eye appointment, then turn it in then. Okay, I'll be leaving campus by 4:15 to go over to the Birmingham East Campus to teach my last class there, and that will be from 5 until 6:30. So I'll be there a little before 5, and I'll be there after 6:30, so you can come bring things there too. That's on East Campus, Ethel Hall building, which is the nursing or health professions building, and I'm up in room 214. All right, then Wednesday, first day of finals for this Monday, Wednesday classes, the only day of finals for Monday, Wednesday classes, and I will be here from 8 o'clock in the morning until 6 o'clock in the evening, mostly down in my office, but if anyone for some reason needs to be up in the classroom to explain something or something, I'll come up here to do so. But I'm thinking I'll be in the office just about all day. Okay? That's Wednesday. Thursday is the finals day for Tuesday, Thursday classes. So I'll be in my office from 8 in the morning until about 4 o'clock Thursday afternoon. At 4 o'clock I got to leave. I got one thing to do on my way to the Birmingham East Campus. So I have to leave a little early to get there, but it'll be from I'll leave this campus about 4 and be there hopefully before 5. Okay, because I've got, like I said, a stop or two to make on the way. One stop, I know of. Okay, so if you haven't turned anything into me by 4 o'clock on Thursday, please take it to the Birmingham East Campus, Ethel Hall building, room 214, between 5 and 6:30. Because that's the last time I'll be on campus until fall term begins. So if I don't have it by the end of business on Thursday, which will be 4 o'clock on this campus or 6:30 on that campus, I'm not going to get it. If you slide it under my door here after 4 o'clock on Thursday, I won't see it until I get back. Okay, and that means you get incomplete until I get back for fall term. Because I'm requesting to take leave the following Monday, and that's next Monday. And if I'm not here to do that, then I'm not going to see your papers till I get back. Does that answer your question, Devin? Okay, good deal. All right. Yeah, we had stepped back and we're going to do example 9. So let's do example 9. Find the antiderivative or the integral of secant x dx. Okay. Now, is that one that we know that's the derivative of something? Anybody? It's not. So we're going to have to come up with something else, sort of like we did last time. What would be the something else you might choose this time? What is secant x? That's 1 over cosine x dx. Okay? And what might you want to do with that? Well, that actually is not going to get you anywhere. Okay? Secant x is one of those that is a real pain in the neck. And they act like anyone would have thought of doing this, and I don't know anyone who would. But what they do, from out of space, or some unknown body part, they say, well, let's multiply by something. Let's multiply by secant x plus tangent x over secant x plus tangent x. Now, who would have ever thought of multiplying by that? Okay? It's just sort of off the wall, out of nowhere. Okay? So what does that give you? If you multiply through by that, what do you get? Numerator to numerator. Secant x times secant x is secant squared x plus secant x times tangent x. Okay? And divide that by secant x plus tangent x dx. Now, notice what that does for you. Or, if you don't notice it, what would you do next? And what substitution would you use? That's it. Secant x plus tangent x. And what do you get next then? Then, what's always your next line? Du is equal to, what's the derivative of secant x? Anyone remember? Derivative of secant x. If you got in front of the book, look at it and see what derivative of secant x is. Okay, the top part of your very inside cover of that first page, there, number 17. What's the derivative of secant x? Okay, we're using x's, so that'll be secant x tangent x. One other thing, dx, right? Well, there's a du right there. Isn't that special? Okay. Oh, but wait. We didn't do the second part, did we? What's the derivative of tangent x? U was secant x plus tangent x. This is the derivative of secant x. What's the derivative of tangent x? Also on the front inside cover. Secant squared x, isn't it? And that's what we have here. So lo and behold, and then this whole thing times dx, that's your entire numerator here. So what we have is the integral of du over u. And what would that be? Log absolute value u. And that, if you plug in what u is, or u are, that would be, oh, and plus c, by the way. Log of absolute value secant x, I can't write, secant x plus tangent x plus c. Now, you need to sort of remind yourself of where these things are defined. Secant x and tangent x are defined between negative pi halves and pi halves for one instance. And in that domain for x, secant is always positive in that domain. Tangent is very negative on one side, very positive on the other side. But secant, I believe, is always greater than tangent. So I believe that always does turn out something positive. So therefore, you could lose the absolute value if you're between minus pi halves and pi halves. If you're between pi halves and 3 halves pi, you have to have absolute value bars. If you're within minus 3 halves pi to negative pi halves, you have to have them. But then if you're somewhere else, you know, every other sequence or interval there would be positive and then negative. Okay, so you have to just keep it in mind. So for safety, they just leave the absolute value in there. All right. Any questions on that? With that in mind, then, here is their review of the integrals of the 6 basic trig functions summarized below Okay, what would be the antiderivative of sine u? Anybody? Help me. Antiderivative of sine u. Negative. The derivative of sine u is positive. The antiderivative is negative, minus cosine u. Plus c, of course. How about antiderivative of cosine u? Sine u plus c. How about antiderivative of tangent u? We just did that, remember? That was the negative log of cosine u, or you could write it as the log of absolute value secant u. Either one of those. Cotangent, it would then be the positive. They always switch signs. Positive log of sine u, and I would leave it that way. Okay. If you did this to the -1, then you could do this positive log of cosecant u. Okay. How about antiderivative of secant u? We just did that one. Anybody remember? Was it that long ago?
Log of
Secant u plus tangent u. And then this one would be the negative log of cosecant u plus cotangent u. Okay, plus c. Do I memorize those? No, I'll look them up when I need them. Okay. I don't think it's worth trying to memorize. You've got tables, use them. Okay. Now, that's the end of the slideshow for 5.2. They do have another couple of examples there, but you know what? I think, since this is the last class, let's just skip those and go to 5.3, which is inverse functions, and this is just going to be a slideshow too. Because what I really want to get to is 5.4. And yes, that is something you'll need in Cal 2. The rest of this, possibly, let's see, why did I hit the wrong button? Okay. We'll discard that and go to 5.4. 5.4 will just be, 5.3 will just be the PowerPoint show. Okay? There is some stuff in here worth maybe remembering, but I wouldn't, either it's, in my mind, sort of straightforward, or something you can always look up if you need it. Okay? Still Chapter 5, logarithmic, exponential, and other transcendental functions. By the way, your trig functions aren't considered, I don't think, transcendental functions, but anyway. Now we're going to talk about inverse functions. Don't feel too threatened by this, because this is something you can always go back and check. We'll verify that one function is the inverse of another function. You did this back in pre-calculus, okay? Determine whether a function has an inverse function. You did that in pre-calculus. And then we'll find the derivative of an inverse function, okay? By a certain way, okay? So here we go, and this again is old review. If here's your function, f of x is x plus 3, that maps from this set, A, 1, 2, 3, 4. If you plug in those for x, x plus 1 is, 1 plus 3 is, 2 plus 3 is, 3 plus 3 is, and 4 plus 3 is 7. So you map into B, which is 4, 5, 6, 7. Okay? Now you can also, that's one way to express that function, mapping using this formula to go from this domain to that range. Or you can list a set of ordered pairs. 1, 4, 2, 5, 3, 6, 4, 7. That's another way to list that function. Okay, pretty simple function, very limited domain, very limited range, set of ordered pairs, just 4 of them. Now, if you were to interchange the first and the second coordinates for each of the ordered pair, you can form what they call the inverse function of f. That undoes what f was doing. F was adding 3 to each one, and this is going to undo that by subtracting 3. If you take 4, minus 3 is 1, 5 minus 3 is 2, 6 minus 3 is 4. 3 and 7 minus 3 is 4. Okay? That's the inverse function, and it's denoted by f inverse. Again, this is all old stuff. Okay? It's a function that goes from what was your range now becomes your domain of the inverse function. What was your domain of the original function becomes the range of your inverse function. So it maps from B to A, and that can be written as f inverse is 4, 1, 5, 2, 6, 3, 7, 4. Set of those 4 values. Okay. Now, note that the domain of the f is equal to the range of f inverse, and vice versa. Okay? The functions f and f inverse have the effect of undoing each other. That's what an inverse function does. That is, when you form the composition of f with f inverse, you're going to wind up with just the identity function x. Okay? So f of f inverse is x, and f inverse of f is x. Because you're starting with x, doing the inverse function of it, and then doing the function of that takes you right back to x. So we start with this and act on f with f on x, and then with f inverse, it undoes that and gets you back to x. Okay. Joy, right? Okay. Now, before you leave, be sure to pick up you turn in all your tests up to now, right? Okay. And did you get a copy of the last test? Okay, good. So pick up your old ones. Now, I can't return your research paper, but by the way, it's due today, but I'll take it later, but you'll start losing points if it's after today. I think you've already turned yours in. Not yet. Okay, well, I need it whenever you can get it. So here's, this is sort of called a mapping illustration. If this is the domain of f, and you operate on it with f, you get into the range, which they call B down here, just like we did earlier. And if you took the inverse of f, it would take the values out of B and map them back into the original A. So the domain of f is A, maps into the range of f, which is B. So that range of f becomes the domain of f inverse, and it maps back into A, which was the domain of f inverse of f, and it becomes the range of f inverse. Okay. So here's the definition of inverse function. Function g is the inverse function of the function f when f of g of x is equal to x for every x in the domain of g. And at the same time, g of x, b operating on f of x is equal for x as well for every x that's in the domain of f. It maps exactly. The function g is denoted by f inverse, in red, the inverse function, f inverse. Okay. Here are some important observations about inverse functions. And by the way, you just came in, we're in 5.3, which is inverse functions. And this is just a slideshow here. Here's an important observation about the inverse function. If g is the inverse function of f, then f is also the inverse function of g. The domain of f inverse is equal to the range of f. We've already said that. And the range of f inverse is equal to the domain of f. We already said that. Number 3, a function need not have an inverse function, but when it does, the inverse function is unique. It only has one inverse. Some don't have inverses, but if it does have an inverse, it's a unique function. Now you can think of f inverse as undoing what had been done by f. For example, subtraction can be used to undo addition. Division can be used to undo multiplication. You did that way back in grammar school. Radicals or roots can undo powers. Powers can undo roots. You know, variety of ones like this. If f of x is x plus c, then f inverse is usually going to be x minus c. It undoes what the previous one did. These are inverse functions of each other. A lot of inverses are a lot more complicated than this, so you can't just look at it and say, oh, that'll be it. If f of x is c times x, f inverse would be x divided by c. Okay? Now, if this is beginning to look maybe a little vaguely familiar, remember, integration is the inverse operation, not function, but operation of differentiation. So if you differentiate it one way, you antiderivative the other way. And remember, if you take the derivative, c times x, that gives you c. The antiderivative of c times x would be, or say of x squared would be x cubed over 3, because you're undoing what you did with the in that case the constant multiple. But these are inverse functions of each other. The others are operations. Now, of course, c can't be 0 here, but c wouldn't make any sense being 0 here either. F of x equals 0 times x, that's 0. You know, if you want to take the derivative of 0, it really has no derivative. Okay. Now, it's fun exercises, but hopefully you've already done this in pre-calculus, how to show that these are inverse functions of each other. What you do is f of g of x, and then do g of f of x. If they both come up to being x, they're inverse functions. So here's how they do that, because the domains and ranges of both f and g. Domain of f, all real numbers. Domain of, excuse me, I'll wake up. Okay. All right. The domain of g is all real numbers, because this is a cube root. If that was a square root, you have to have what's in there positive. Cube roots can be anything. So the domains and ranges are all real numbers. They consist of all real numbers. You can conclude that both composite functions exist for all x's, so do the composites. The first will be f of g of x, that would be this function, 2 times whatever's inside here. Well, whatever's inside is g of x. So it's 2 times the cube root of x plus 1 over 2, then cube that and subtract 1 from it. Well, if you do what they told you to, you take the cube of a cube root, that undoes that, and that leaves you x squared, or x plus 1 over 2. Divide out the 2's, and that gives you x plus 1 minus 1, that gives you x. Okay? So that certainly produces x. Okay, and here they showed it. Cubing the cube root just gives you what's inside, multiplying 2 over 2 is 1, and that would be x plus 1 times x plus 1 minus 1, and that just becomes x. But that's only half of it. You have to do the other half too. G of f of x. Well, g is the cube root of, and the x here, you plug in what was an x here, you plug in f of x, which is 2x cubed minus 1. Plug that in here, and then g takes whatever that x is, cube root of x plus 1 over 2. So it would be this thing plus 1 over 2. Well, 2x cubed plus 1 minus 1, that goes to 2x cubed, divided by 2, and you get the cube root of x cubed, and the cube root of x cubed is precisely x. So here's what they did. First, remove parentheses, combine the plus 1 and minus 1, that goes to 0, then that over that is cube root of x cubed, and cube root of x cubed is precisely x. So those are inverse functions of each other. Because these are indeed inverse functions of each other, you can conclude they're both inverse functions of each other, and here's a characteristic of inverse functions. If you were to graph them, now this one is taking the cube root function that usually passes through the origin here, but it's because it's has 1 added to it, you move it to the left 1, and then you have a vertical strength expansion by 2. Okay, so anyway, this is what that cube root function looks like. The cubing function, well, first you adding 1 is going to move it down the y-axis by 1, and then the multiplied by 2 is a vertical stretch, and that gives you this function. And if you look at that, here's your identity function, y is equal to x. And this is a mirror image. F and G are mirror images of each other. Where they do cross, it's on that y is equal to x. 1 is equal to 1. That works here, works here, okay? And all the others are exactly mirror images of each other. Interesting things to note, if f is an increasing function, g also is an increasing function. If f was decreasing, g is decreasing. That f nor g can both increase and decrease because then they won't work. And we'll see that just now. That sneeze has really loosened everything up. I may have to take a break in a minute just to clear my head. So in that figure, we saw the graphs of f and f inverse, f and g, which is f inverse, appear to be mirror images of each other with respect to the identity function y is equal to x. The graph of f inverse is a reflection of the graph of f across y is equal to x. So this idea is generalized in this theorem. The graph of f contains the point AB if and only if the graph of f inverse contains the point BA. Well, that's exactly what we did. We just, when we had a function, we just interchanged the x and the y to get its inverse. And that's exactly what we get here. Okay. So let's talk briefly about the existence of the inverse function, because I think you've already had this before in pre-calculus algebra. This is a review. Not every function has an inverse function. Theorem 5.6 suggests a graphical test for those that do, and this is the horizontal line test. Remember, vertical line test just determines whether a function was a function or not. If a vertical line crossed a graph more than once, it wasn't a function. Okay? Well, if the graphs are then going to be mirror images of each other, then this would flip up this way. Okay? And if it did, then it wouldn't be a function, because flipped up this way, the vertical line test wouldn't work, because written this way, the horizontal line test doesn't work. So that gives us an additional test to tell whether a function has an inverse or not, the horizontal line test. If a horizontal line intersects the graph more than once, not a one-to-one function. So here they've introduced the one-to-one before they told you what one-to-one is. So here's this theorem that formally states why the horizontal line test is valid. A function has an inverse function if and only if it's one-to-one, meaning it's either increasing or decreasing. It can't back up on itself. Then it would fail the horizontal line test. If f is strictly monotonic, meaning strictly increasing over the entire domain or strictly decreasing in the entire domain, then it's a one-to-one function. Therefore, it has an inverse function. This one is increasing for part of the way, decreasing for part of the way. Not a one-to-one function. Does not have an inverse. Okay, so this one, x cubed plus x minus 1, appears to be increasing everywhere in its entire domain. It does have an inverse function. That would be a lot more difficult one to find. Okay, if it's just adding, subtracting, multiplying, dividing, this is cubing and doing stuff. It's a little bit harder to find. Because f is increasing over its entire domain, it has an inverse function. To verify this, note that the derivative, f prime, is 3x squared plus 1. 3x squared plus 1. And that is always positive for all real values of x. So that means f is an increasing function because its first derivative is always positive. Okay. So f is strictly monotonic, meaning always increasing. Oh my goodness. 10 o'clock scholar. Okay. Ryan's here. I'm sorry, the 30 scholar. Okay. By the way, before you leave, pick up all your old tests. If there's any tests you haven't turned in yet, get it in. And if there's a paper you haven't turned in yet, give that to me as well. I can't return your research papers, but I can return your older tests. I need to have them today. Okay. research papers to keep you from losing points. I will accept them later, but they'll lose points. Tests, though, have to be in today. Okay, that's your first 3 tests, not your final. Yeah. Okay. All right. So, F is strictly monotonic, must have an inverse function. And they haven't told us now how to get it, but you had that before. All right, because Ryan just came in, let me review quickly. This is backing up a little bit, but let me review quickly what the rest of the week looks like. I'm in class today until 5:30, office hours 5:30 to 6. Good to turn in things anytime there. Okay, tomorrow, last day for Tuesday, Thursday classes, so I'm in the office from 8 to 8:30, in class from 8:30 to 10:45, in the office from 10:45 until about 4:15. At that time, I have to leave to go to the Birmingham East Campus to teach my last class there. Okay, so if you do want to catch me there this evening, I'm on Birmingham East Campus, Ethel Hall, Health Professions Building, room 214, up on the 2nd floor. Okay, so that's tomorrow, last day of class for Tuesday, Thursday classes. So Wednesday, final exam day, I'll be in my office, room 265, just down the hall here at the end of the hall. Go down that half flight of stairs, into the hall, last office on the left is 265. That's where I'll be. If I'm not in there, you can slide it under my door. If I'm not in there, I'll be back sometime soon. But that's Wednesday. Oh, let me back up one. Tomorrow, I have an eye appointment at 2:30. So if I'm going to have to leave campus between 2 and 2:15 to get across the street to the eye appointment. As soon as they finish, then I'll be back, but then I'll be heading to the Birmingham East Campus by 5 o'clock. I'll leave here by 4:15. So that's tomorrow. Wednesday then, all day in my office, 8 to 6. Okay? So come bring in me your last test, your final exam, anytime there, and I'll possibly be able to grade it on the spot, but if not, I'll let you know what it's coming out to be. Now, Thursday. Thursday is my last day on campus until the fall, I hope anyway. I'm requesting leave for next Monday. That's normally our last day. So if you don't have something to me by Thursday, I'm not going to get it until I come back for fall term. So that means you're getting an incomplete. If it's your research paper or your last test or something like that, if I don't have it by Thursday. So Thursday office hours are really important. Thursday, I start here at 8 o'clock, and I'm here till close to 4 o'clock. I've got to leave shortly after 4 o'clock to head to the Birmingham East Campus. I'll be there from 5 to 6:30. So if you turn in anything to me on this campus after 4 o'clock on Thursday, I won't see it until I come back for spring break. For fall term. If you don't get it to me by 6:30 over on the Birmingham East Campus, again, Ethel Hall Building, room 214, I won't get it. And don't take it over there and leave it somewhere, because I don't even know if that class is going to make next term, so don't know.
So office hours for Thursday.
For Thursday. On this campus, 8 to 4.
8 to 4.
And on that campus, 5 to 6:30.
Room number?
214 on the other campus, 265 on this campus. Okay?
So
And
what time are you here till today? 5 or 6?
Say that again.
What time are you here till today?
I'll be here until 6 o'clock at least. Probably a little past 6, but at least until 6. Okay? I have class all day today till 5:30 or 5:25, and then I'm here at least 5:25 to 6 o'clock. I'll be up here for part of that time, and then my office will be on the part. So anytime today up until 6. If you don't catch me before 6, slide it under my door. I'll get it first thing tomorrow morning. Okay? All right. Any questions about how we wind up things? Okay. Now, from the graph of this one, x cubed minus x plus 1, notice how similar they were. That was x cubed plus x minus 1. That's a 1-to-1 function. x cubed minus x plus 1 is not a one-to-one function. It fails the vertical line test in several places in between here and there. Okay, anywhere here it fails the horizontal line test. Not a one-to-one function. It does not have an inverse, at least in its entire domain. In other words, it's not one-to-one, and for instance, f has the same value when x equals -1, 1, and 0. All have values of 1 there, not one-to-one. So by theorem 5.7, not a one-to-one function, and does not have an inverse. But, yeah, sure. You might have to pick it up and just rub it on your
Yeah,
hand.
I know how it goes.
Yeah.
No finesse.
Okay. The following guidelines suggest a procedure for finding an inverse function. And again, this is pre-calculus algebra stuff, so I'll let you see the work one, but here's the steps. Okay? First, figure out whether it's inverse or not. Is it a one-to-one function? If it's strictly increasing or strictly decreasing, it is a one-to-one function. If it's not a one-to-one function. It doesn't have an inverse. So that's the first step. Second step is solve for x as a function of y. Now, back in pre-calculus algebra, they actually first had you exchange the x and y. This one has you solve for x as a function of y and then exchange. Whichever technique you use, it winds up being the same thing. The resulting equation is then y is equal to f inverse. Define the domain of f inverse as the range of f. Okay, verify that they are. Take f of f inverse, you better give you an x. Take f inverse of f, and you better get an x. If you don't get an x both ways, you've either made an error somewhere or it wasn't an inverse to begin with. So I'm not going to work this one, but what we would do is first make this. Okay, first, is that a strictly increasing function or decreasing? It is strictly increasing because for all values in the domain, which would be for this, 2x minus 3 has to be greater than or equal to 0. So 2x has to be greater than or equal to 3. X has to be greater than or equal to 3 halves. Okay?
You have a negative number in absolute the square root units?
Okay? Like I just said, the argument of the square root has to be greater than or equal to 0. Right? Yeah. And when you do that, you find out that x then would have to be greater than or equal to 3 halves. Okay? So any x that's less than 3 halves, you wind up with a negative number here. So be sure you're greater than or equal to 3 halves. Okay? But then, once you do the absolute value, the square root function, starting at 3 halves, 1 1/2, you'll see that it's always increasing. It's the half of a parabola, always increasing. So that would be a one-to-one function on its domain for x greater than or equal to 1.5. Okay? So you first find that out, and then how do you find what the inverse function is? Well, in pre-calculus, they said first change that to y. So do that. Y is equal to the square root of 2x minus 3. Then exchange the variables or solve for x. It doesn't matter which way you do, and then exchange variables, and that then becomes your f inverse. So this is the same author that wrote the pre-calculus algebra text. He just swaps those two, the order of those two between the two books. Okay? From the graph, here is your square root of 2x minus 3. See, it starts at 1 1/2, goes up from there. Well, flip this over here, and you start at 0, 1 1/2 here. This is 1 1/2, 0 here, and then it goes up from there. Both of them are strictly increasing functions, reflections across the line y is equal to x. Okay? how you check to make sure this is strictly increasing, they say take the derivative of this, and that'd be 2 times this thing to the minus 1/2. And you have a minus 1/2 of that, or 1/2 of that, because this is to the 1/2 power, and the 2 and the 1/2 cancel out. And sure enough, this is always increasing because this is a positive number only, okay, in its domain. In its domain, that's always a positive number. 1 divided by a positive number is a positive number. Okay. F is strictly monotonic. It must have an inverse, and its inverse. So here's how they go about finding the inverse. The other was taking the derivative. This is finding the inverse. They set y is equal to f of x. Okay. Now, what they used to say is exchange the x and y now and then solve for y. What they're saying now is solve for x and then exchange. It doesn't matter which way you do it, but they are solving for x first, squaring each side, and then adding 3, dividing by 2, and that gives you x is equal to this. And then they said flip them and make y equal x squared plus 3 over 2, and then make that your F inverse. Okay. And that then the domain of F inverse is the range of F, which was 0 to positive infinity. The domain of F inverse. If you go back and look at the graph, the domain of F is from 1.5 to positive infinity. The range of F is from 0 to positive infinity. So that makes the domain of F inverse from 0 to positive infinity, and the range of F inverse from 1.5 to positive infinity. So the domain and range exchange with each other. You can verify that result by then doing F of F inverse, which is not one we did before, I don't believe. So the F function says take the square root of 2 times whatever's inside the parentheses. That happens to be your F inverse here, x squared plus 3 over 2, and then subtract 3 from that. That's the last part of your F function. Well, if you divide out the 2's, then you have x squared plus 3 minus 3. The 3's add to 0, and the square root of x squared is x. Okay? That's what they did here. And then if you do F inverse of F inverse was squaring the x, but here instead of x you use F inverse, you use F, which is 2x, square root of 2x minus 3. So that's what you square, add 3 to it, and divide by 2. And when you square this, you get 2x minus 3 plus 3. Those add to 0. The 2's cancel out, and you wind up with just x. The square root of x squared is x. All right. You're given a function that is not one-to-one in its domain. By restricting the domain to an interval in which the function is strictly monotonic, you can conclude that the new function is one-to-one in the restricted domain. All right. For instance, f of x equals sine x. Well, all of you, I hope, know sine x does this. Right? Up and down between 0, minus 1, and 1 forever. Well, obviously, that's not monotonic because it's going up half the time, going down half the time, going up half the time, going down half the time. Not monotonic. But if you restrict it to minus pi halves to pi halves, inclusive, then it's increasing here and starts to decrease there, but it's increasing the entire domain of minus pi halves to pi halves. There it is strictly monotonic. And it's also monotonic from pi halves to 3 halves pi, but there it's strictly decreasing from minus 3 halves pi to pi. So you can choose different pieces. This is the one we use sort of the standard, negative pi halves to to pi halves. It is monotonic there. So sine in general is not always 1-to-1, but if you restrict that, it would be. Because sine, say, at 0 would be 0, sine at pi is 0, sine at 2 pi is 0, so there's multiple places where it has the same value. But if you restrict yourself to the range from negative pi halves to pi halves, the derivative there is cosine, and cosine is always positive, from minus pi halves to pi halves. So therefore the sine is monotonically increasing. Okay. Finally, because the left and right endpoints correspond to relative extrema, you can conclude from your minimum here to your maximum there, always increasing in between. That is 1-to-1 on that interval, minus pi halves to pi halves. So, now this is the part I guess they brag about, okay? I've been turning the derivative of an inverse function. In this form, I seldom, if ever, use. It's there to be used if you need it, but generally, you don't need to necessarily think in these terms. The next two theorems discuss the derivative of an inverse function. First, continuity and differentiable of an inverse function. If f is a function whose domain is the interval I, and if f has an inverse function, that meant the following statements are true. If f has an inverse, its domain is I, f has to be continuous on that domain. You don't have any gaps or breaks in an inverse function, okay? Then f inverse is also continuous in its domain. If f is continuous, then f inverse is continuous. If f is increasing in the domain, f inverse is increasing on its domain. If f is decreasing in its domain, f inverse is decreasing on its domain. If f is differentiable on an interval containing c, and f prime of c is not equal to 0, then f inverse is differentiable at f of c. Well, that's a new one you wouldn't have had in pre-calculus algebra. So, what is that derivative then? If f is a function that is differentiable on an interval I, if f has an inverse g, and that g is differentiable for any x for which f prime of g of x is not 0, then g prime is 1 over f prime of g of x, as long as that f prime of g of x is not equal to 0. Okay? Now, again, there may be times that you might find this useful. I've never run into many of them. Okay? That's a definition for what your inverse function is. Now, let's just show how they did this. First, here's f of x is equal to 1/4 x cubed plus x minus 1. And they ask for what's the value of f inverse when x is equal to 3. Well, you would basically have to find the inverse of this and then plug that in. It says that what is the value for f prime, the derivative of the inverse of that when x equals 3. Well, if you found this one out, then, well, let's just watch how they did it. Okay? Notice that f is 1-to-1 and therefore has an inverse function. Now, I can't look at that and tell you that's true, but they did. You can do this. Take the derivative of this, okay? The derivative of this is 3/4 x squared plus 1. Yes, that's positive everywhere, so this is a 1-to-1 function. Notice we have that tool we didn't have back in pre-calculus. You can take a derivative now and see if it's always increasing or decreasing. Always positive or always negative. Because f of x is equal to 3 when x equals 2, you know the f inverse of 3 is 2. Okay? Thing is, how do you know the first part here? Okay? Says what is the value of f inverse when x equals 3? Okay? You would have to do a lot of plugging and chugging to come up with that. So this is all true here. Okay? And because it is differentiable, it has an inverse function, and you can find that other theorem that G of equal F inverse. And basically, since you know that it's true about the values, then the F prime at 3 is 1 over F prime of F inverse prime at 3 is 1 over F inverse of F prime of F inverse of 3. And that would be F prime of 2, and then just plug in and see what 1 over F prime of 2 is. Again, it's sort of a complicated formula. I don't really, in many instances, find any use for it whatsoever. It's true, though. It's absolutely true. Okay? Moreover, using F prime is equal to 3/4 x squared plus 1. We had already done that to determine that it's strictly increasing because this is always positive. Just plug in 2 for this, and that would give you 2 squared is 4. That would be 3 plus 1 is 4. And that would be 1/4. 1 over 4 is 1/4. Okay. In example 5, note that blah blah, the slope of the graph is 4. At the point 3, 2, the slope of the graph is 1/4. The slopes reciprocate. They don't negate, they reciprocate. Okay? This is 4, that's 1 over 4. Both of those are always positive. And these are strictly increasing functions, they better be positive. Okay? Slope here of this one is 4, of this one is 1/4. In general, if y is equal to g of x, and that is also f inverse of x, then f of y is equal to x, because f of f inverse is x, and f prime of y is dy dx. So it follows from that g prime is dy dx. That's 1 over f prime of g of x. It's 1 over f prime of y. That's 1 over dx dy. So bottom line is, if this is derivative of your f function, okay, then 1 over that is the derivative of your inverse of f, okay, like we showed earlier. Okay. Now, f of x equals x squared. Is that a one-to-one function? What's the effect of that? F of x equals x squared. It's a parabola. Parabola, no, not one-to-one. However, if you restrict yourself to x positive or x negative, either one, then it would be. Okay? Now, the inverse function of that would be the square root of x. Okay? That undoes the squaring function, as long as x is positive. So we had to restrict ourselves to positive x's. Show that the slopes of the graph are reciprocals of each other at the following points. Well, you can take the derivative of this, and that would be 2x, and x equals 2. 2 times x would be 4, okay? And square root of 4, that's 2. So take the derivatives of that. That would be a derivative of 4, and when you took the derivative of that, would be 1/2 of 1 over x squared. And when x equals 4, then that would be 1/2 of 1 over 2, which would be 1/4. And this would be a 4, so that was a 1/4. So yeah, it works. You could, well, let's watch them do it. Derivative of f and f inverse are, we just did that 2x for this one, and 1 over 2 times square root of x for that one. at 2,4, the slope of f is 4, and the slope of f inverse is 1 over 4. Okay, we can do the same thing for 3,9 and 9,3. The slope of that would be 2 times 3 is 6, and for the slope of this one would be 1 over 2 times square root of 9, which would be 1/6. 1 over 3 times 3, which is 1 over 6. In both cases, the slopes are reciprocals as shown here. Here is your square root function. There's the square root function. As long as you restrict the domain to the place where they're monotonic, strictly increasing, you got it. Whew. That was the end of 5.3. Okay, let's move quickly to 5.4. And this, I think, will probably be the last thing we do. Because to me, this is the most important thing of what we've got left. Okay. Chapter 5, logarithmic, exponential, and transcendental functions, other transcendental functions. We're going to focus now on exponential functions, differentiation, and integration. Now, we'll develop properties of the natural exponential function. They really draw this out, okay? We'll differentiate natural exponential functions, and frankly, you'll find out this is my favorite function of all time. We'll integrate natural exponential functions. It's my favorite function to integrate of all times because it's so simple. So let's look at the natural exponential function. The function f of x equals log x is increasing on its entire domain like this, and therefore it has an inverse function, f inverse. The domain of f inverse is a set of all real numbers. Why? Because the range of log x is all real numbers. But the range of your inverse function is only greater than 0 because your domain of log is only greater than 0. Okay? So the domain of f inverse is a set of all real numbers. The range is a set of all positive real numbers because that's the domain of your inverse function. It's shown here. And these are strictly increasing, both of them. Okay. So for any real number x, f of f inverse is equal to, now f was the log function, and log of f inverse has to equal x. So x is a rational number. Now if f is a rational number, then, okay, here is the most important thing to note here. The inverse function of your log function is your exponential function. So know this. Log of e to the x would then be x times log e. Log of e is 1. Know that, and that's equal to x. So that's true for any rational number x. Frankly, it's true for any number as x. Rational for sure, but because the natural logarithmic function is 1 to 1, you can conclude that f inverse and e to the x have to agree for the rational values of x. If they agree for the rational values of x, they're also going to agree for the irrational values of x, because you can't just pick and choose in there. All right, so this next definition extends to the meaning e to the x to include real values. Okay. Again, to me, this is tedious. There are, to me, much easier ways to do this. But this is how he's choosing to do it. The inverse function of the natural logarithmic function, f of x equals log x, is called the natural exponential function, and is denoted by f inverse of, when f is log x, f inverse is e to the x. That is, y is equal to e to the x, if and only if you take the log of both sides, log of y would then be equal to x equals log y. Okay? The inverse relationship between the natural logarithm and its natural exponential function can be summarized this way, And this, by the way, is always true. The log of e to the x, just like we did before, bring the x on the outside is log of e is 1. So that would be x times 1. But also this one, e to the log x, if you, that's also equal to x, because they are inverse functions of each other. Okay? So this one we know has to be true. That one, because they're inverse functions, it also has to be true. Later, we will be using both of these to solve pretty complicated equations, because you can undo a log with an exponential and undo an exponential with a log. So let's do this one real quickly. Can we solve for that? What might we choose to do? Let me get my pen set up. Again, this is not quite where I want to be yet, but let's just do it because you need to understand these concepts. Anyone want to guess what we might do first? Say again? Okay, not in this case. We haven't learned what the derivative of exponential is yet. Later that would be a great idea, but we haven't talked that yet. Take the log of both sides. So that means the log of 7, natural log of 7, is the log of e to the x plus 1. Oh, wait, I didn't write that right. E to the x plus 1. Said it right, but wrote it wrong. Okay. Now, log 7 is just a number. Log 7. That's equal to, you can then bring the exponent down front, and that would be x plus 1 times the log of e. Does anyone know what the log of e is? 1, yeah. A log undoes, yeah. So that would be 1. So this would be log 7 is equal to x plus 1 times 1, okay? And then you do x is equal to log 7 minus 1, okay? So that tells you what value. Now, hint. If e to some number is equal to a rational number, that number you started with has to be irrational. I mean, this is just a little, happens to be true, okay? And sure enough, e to that number, whatever it is, has to be, that is a rational number, 7, and that number that you started with is an irrational number, log 7 minus 1. So that's just a little factoid, okay? You can convert from exponential form to logarithmic form, taking the natural log on each side of the equation, and that would be log 7 is equal to that, and so that's exactly what we got. Log 7 is equal to x plus 1. Subtract 1 from both sides. X equal log 7 minus 1. And you can fill that in, calculate, see what it comes up to, 0.946. Okay, so here's how you check it. Put the minus 1 times plus log 7 in instead of your e. Okay. Now, what they sort of skipped over here, e an exponent, a base raised to a power, if that's a sum or a difference, that's the same as e to the log 7 minus over e to the 1. Well, e to the 1 is 1, and e to the log 7 is 7. So it does work out. They skipped way too many steps there. I would have interjected this one as e to the minus 1 times e to the log 7 plus 1. And e to the minus 1 is 1 over e plus 7. Huh. Oh, sorry. That's times right here. And then this thing here is plus 1. No, that's not right. Sorry. I've lost there. Oh, let me erase all that. I wasn't going to do these problems, but here I wound up doing it. Okay, this is still up in the exponent. That's why it's messing up. E to the x minus plus 1. If x is equal to my pen has gone away. There we go. Okay, so this is 7. The question is that equal to e to the minus 1 plus log 7 plus 1? Okay, well, minus 1 plus 1 is 0, so it is e I'm sorry, I can't even read my own writing here. Okay, those go out, and this is a e to the log 7. Goodness gracious, where's the pen? There. Is that equal to e to the log 7? And sure enough it is. 7 is equal to e to the log 7. E undoes the log, log undoes the e, so that leaves you 7, and that is correct. So they skipped a lot of steps real quickly, but they were pretty basic. Okay, so let me erase mine. They did them, but they didn't really show them that well. It's just that this is minus 1. This was your x from the previous slide, and so you plug that in here. Minus 1 plus 1 adds a 0, and then gives you e to the log 7, and sure enough, that is 7. So it does check. So familiar rules for operating rational exponents can be extended to the natural logarithm, natural exponential function. And here's some of these, and these ought to be old hat to you as well. If a and b are any real numbers in the world, e to the a times e to the b, anytime you're multiplying two bases, different exponents, keep the base, add the exponent. E to the a plus b. Or dividing two exponents, same base, different exponents, that's e to the a minus b. Now here, I would have been tempted to put that in parentheses. Makes it a little more obvious. Okay. Now, I'm losing my voice for some reason, I don't know why. Inverse function f inverse shares many properties with f, so that the natural exponential function inherits the property listed below from the natural logarithmic function. And here's you're here for the next class, aren't you?
Yeah, I want to turn this in.
Oh, okay. All right.
That's the
Yeah.
text in the paper. That's it.
Okay, you got it. Good deal. did you get my, did you get my email? Oh, okay, yeah, you must have, that's what I sent you, wasn't it?
Yes, sir.
And, okay, thanks. All right. So, he's not in this class, okay. All right. Domain of e to the x has to be all real numbers because the range of log x was all real numbers. The range of e to the x is only positive numbers because the domain of log x was only positive numbers. The function f of x equal e to the x is continuous because the log in its domain is continuous. Okay? It's increasing because the log was increasing. It's 1-to-1 because the log was 1-to-1. The graph of f of x equal e to the x is concave upward on its involved entire domain because the log was concave downward on this entire domain. The limit as x approaches negative infinity has to be 0 because it's always positive but getting less and less and less, so it has to be 0. The limit as x goes to positive infinity of e to the x is going to positive infinity. Okay. Just certain characteristics. Okay. Now they're staying with inverse functions. Again, this is the part, okay. Now, derivatives of exponential functions. Okay. This to me is the important part. Sorry. And all right. Oh, I'm sorry. I changed the section, but I hadn't changed my, I hadn't turned the page. Okay, we're on page 344 now. Okay. One of the most intriguing and useful characteristics of natural exponential function is that it is its own derivative. Like I said before, it's my favorite function of all time. The derivative of e to the x is e to the x. This is the main thing I wanted you to hear in today's class. In other words, it is a solution when the differential equation says y prime is equal to y. That's going to be the exponential function. Okay, and this is what theorem 511 says. Let u equal be a differentiable function of x. D by dx of e to the x is e to the x. And d by dx of e to the u is e to the u times the u dx. Okay, chain rule applies here. Doesn't here because this is derivative with respect to x of e to the x is e to x. Derivative with respect to x of e to the u would be e to the u. Chain rule du dx. Okay. And makes it one of the most useful functions. In fact, to me, this is what makes it the natural base of our number system is e. Not base 10. Base 10 is counting and doing all your arithmetic things. Base 10 is perfectly fine. Calculus, this is what works. You integrate it, you differentiate it, it all comes out e to the x. So let's just do this. These are important, so let's do them. What do you reckon that would be? D by dx of e to the x, e to the 2x minus 1. Derivative of exponential is the exponential, e to the 2x minus 1, times chain rule times 2. Perfect. Okay? Because that's the derivative of the innermost part. The innermost part, the derivative of that is 2. Okay? Well, I thought they were going to print theirs underneath. They didn't. Whoops, that's not what I wanted. That's what I wanted. Okay. So that's e to the u du dx. E to the u is e to the 2x minus 1 times du dx is 2. So that would be 2e to the 2x minus 1. Okay, how about this one? D by dx of e to the minus 3 over x. What would that be? Anybody? Certainly would be e to the minus 3 over x, because it's times the derivative of 3 over x, right? What would that be? D by dx of minus 3 over x. We'll write that as x to the minus 1, right? And what would that derivative be? 3 over x squared. Okay, so that'd be 3 over x squared. Okay, that's not what you said before, was it? Okay, I didn't think so. I got to thinking it sounded close to that, but I never heard the square in there. Okay, so I think I'm going to have to erase again to show what they do. That'd be e to the u du dx. E to the u would be e to the minus 3 over x, and that's then times e over x squared, which is exactly what we got. Now, that's one way to write the answer. Another way could have been like this. 3 over x squared e to the 3 over x, because the minus sign can move that down into the denominator. That is an x. It looks like a 4, but that's an x. You don't have to do that, but it's just another way you could write it. Okay? Now, what would this one be? Yeah. Is it time? Okay. All right. Sorry. Got carried away. All right. I meant to get this far, so let me get it just to say. The integral of e to the x dx, guess what that will be? If derivative of e to the x is e to the x, the antiderivative of e to the x is also e to the x, in this case plus c. Okay? So exponential functions, so wonderful. Their derivatives are themselves, the integrals are themselves. Now, when you have to unchain rule it and chain rule it, you have to account for those things. But there's the key. Know those. When you go to your next class, know those. The best, easiest, nicest functions going. All right. That's it. Enjoyed having you in class. And let me hit this. Did anyone else come in since I made all the announcements? You've all heard them. Okay. Then get the stuff to me. A lot of people have gotten stuff to me today. Thank you for that. Get your finals in, and if you haven't got it turned in your research paper, get them to me today, preferably. After today, you start losing points. Okay? Good deal. Any questions? Been a great class. Attendance right at the end sort of fell off a little bit.